Thank you, Mr. Chairman. I'd like to talk about some of the work we've been doing, looking at the single-step method in New Zealand. And this is really a very short summary of some of the work that's gone on in the last 6 months. Did that work? Oh, that one. So, by way of introduction, we've heard already this morning about the single-step method that simultaneously uses phenotypic, genomic, and relationship information. And basically what we're doing here is we're augmenting a pedigree-based relationship matrix by a genomic relationship matrix. At the last World Congress, Ignazi talked about controlling inflation by scaling this augmented relationship matrix. And finally, you include this augmented relationship matrix, obviously, in your mixed model equations. Pushing the wrong button. So the aim of our study was to see if we could run the single-step method for the National Genetic Evaluation for the production traits in New Zealand. It's an crossbreed evaluation. We use a random regression testo model where we have an order 3 Legendre polynomials for both additive and permanent environment effects. We include multiple lactations as separate traits, so we have 4 traits for our additive genetic effects, and we have 6 traits for our permanent environment effects, and we have approximately 550 million equations to solve. In terms of the crossbreed evaluation, as we heard earlier this morning, you have to make adjustments to the relationship matrix to account for multiple breeds and their crosses. So we did this in 2 ways. The first way was we did a method that is very similar to what was described this morning, where we adjusted the genomic relationship matrix for breed fractions on allelic frequencies and their variances, and we also took account of the different means of the base populations relative to the traditional relationship matrix. The second way was that we used a Euclidean distance matrix in a Gaussian kernel. And the reason we did that is that is nice and that doesn't require any knowledge about the breeds, which is not a big issue with sires, but when we want to put cows in our model, it could be a big issue because we realise that some of our breed identification for our cows can be a little dodgy, to say the least. So in terms of the methods, we assessed the effect of including the genomic information by comparing traditional breeding values without genomics with GEBVs. The traditional breeding values were from our latest National Genetic Evaluation of May 2012, and the genomic breeding values were from the one-step method, calculating using data up to the end of the 2009 season. And so we had about just over 500 test sires that had their first crop daughters in the 2010 and 2011 season preceding when we ran the one-step method, and that gave us a, if you like, a training and test populations. And of those 500 sires, they were made up of about 250 Holstein Friesian, 104 crossbred bulls, and 170 Jersey bulls. In terms of the data that we were working with, we had 172 million testo records, about just over 20 million animals, and those animals were 50% Holstein Friesian, 18% Jersey, and 29% were crossbreeds between those 2 groups. And we had 5,400 sires genotyped on the Illumina 50K chip, and after editing SNPs, we used about 38,000 SNPs. So when we came to actually calculate the augmented relationship matrix, which is given here in this equation, we scaled it by a series of factors, and for this talk we'll talk about 3 of those factors for the genomic relationship factors and 3 factors for the Euclidean distance matrix. I won't go into the choice of those scaling factors, but we've done a whole lot of prior research to work out kind of an optimal range for those factors. In terms of our computational strategy, we used a preconditioned conjugate solver and iteration on data and data recoding to solve the equations. We pre-calculated that quantity in the equation there, At the moment, we're using direct inversion using the Intel math libraries, which is extremely fast. We have a prototype method that doesn't require inversion, but in that instance, we actually have a PCG running within a PCG, which can get a bit mind-boggling. And in terms of the actual routine solving of the equations, that last equation is basically what is done, which is just simply a matrix times a vector multiplication across traits, and so it's actually extremely simple to include in your current genetic evaluation. So in terms of results, all the models converged within about 500 iterations. Our iteration time was about 2.5 minutes. Adding genomics into the scheme of things only added 5 seconds per iteration, so it didn't really make much difference at all. We had inflation of GVVs regardless of whether we used GRM or the Euclidean distance matrix. And as you'll see, the degree of inflation varied by trait and breed of the test size. So in this graph here, we have two colours, one representing the GRM and the blue representing the Euclidean distance matrix. On the bottom scale, we have inflation. Obviously, you're trying to get an inflation of no inflation, which would be a value of 1. And in some instances, we got overinflation or deflation. But we can see that in terms of inflation, and this is for fat yield, that the Euclidean distance matrix does do a better job of controlling inflation compared to the GRM with different lambda values. I'm not going to go through all the results. If you want the results for the other traits, they're available in the paper. In terms of accuracy, and this is protein yield here, but this could also be for milk yield and fat yield, there's very little difference between A, the lambda values you use, or B, the type of matrix you use. We tend to get very similar accuracies no matter what. In terms of the different breed splits, we tend to get higher accuracies in terms of the correlations between the traditional breeding values in 2011 and the EPV, the genomic breeding values calculated in 2008. Up to correlations are close to just above 0.8, and we get slightly lower values, about 0.6 for the Jersey and Holstein breed. So in terms of those results, we can see that for all traits and for the breeds of size, inflation increased as the scaling parameter increased. In some cases, we got inflation greater than 1, so we actually got deflation, and they were typically for the Holstein Friesian Jersey crossbred sires. The largest differences were between the two genomic relationship matrices that we used, and the largest differences in terms of changes in inflation were observed for fat yield. And augmenting the relationship matrix, the GRM versus the EDM, had very little effect on the accuracy of the evaluations when we came to do the test, looking at test size. One of the issues we do face within the crossbreed evaluation is that a single value of a scaling parameter across breeds is really a compromise. We could work out a weighted factor that would give us a unity inflation across animals regardless of breeds, but in that case we'd still have some breeds, typically the Jerseys, being inflated and the crossbreds being deflated. When we looked at the correlations between the genomic breeding values of the test size, we found that the correlations ranged between 0.9 and 0.99 when we varied those inflation factors, so they're fairly highly correlated. In terms of the proven bulls, the correlations were very high between the different relationship matrix and the different inflation factors. In some cases, it was difficult to tell the evaluations apart for those proven bulls. So in conclusion, so the single-step procedure outlined in this paper was computationally feasible for a complex model and a large amount of data. Given a decent-sized computer, it can run in a reasonable amount of time. We found that augmentation of the relationship matrix with the Euclidean distance matrix tended to give us lower levels of inflation, and the choice of optimal scale parameter will be more challenging in a crossbreed evaluation compared to single breed evaluations. Thank you.